Hey guys, last time we wrote down or we applied the work energy theorem to the problem of an object sliding down a ramp, and we saw that there needed to be a dot product involved. Today, or in this video, I want to describe the concept of power and then also write down the work energy theorem in its full glory, the full 3D version. And I don't really want to solve a problem with it here. You write it out, and you set it up, and you solve it. But you should see it what it is. All right. So the concept of power. Work is the energy added to a system over time. Now, that's okay if you have something which is over a certain interval, like 1 second, 2 seconds. But think about your light bulb or something like that. There's energy. The light bulb is glowing. Okay, so that means it's sending energy into the room all day, every day, day after day. Who cares what the total amount of energy is? I mean, so if somebody says, oh, the light bulb has released 4 million joules, I don't know, whatever. So what? If most of that happened 100 years ago, it's not my problem. It has nothing to do with what's happening right now. So a related quantity to work is the idea of power. Power measures the energy per second which is being delivered. So it's the energy right now that you're receiving, energy per second you're receiving, as opposed to work, which is the energy over an extended amount of time. So I want to go back. The formula for power and oftentimes it's called P. In Physics 1, I tend to explicitly, let me lower this to the player is too strong. Sometimes people write P. And the units on this are going to be something called a watt. And which is really the same as a joule divided by a second. Okay. So power measures the time rate of change of energy being distributed. And right now I'm thinking of it as a time derivative of work, but later on we can have power associated with other types of energy. It's always some sort of a time rate of change of an energy kind of quantity. Okay, so to figure out what there's a really convenient, simple, easy, you should like this formula for power when we're talking about motion. And that comes from the following. We're going to define power to be the time derivative on work. So it's the time derivative on the work. And we're going to think of the work as being the work evaluated between times t and some initial time. All right? So if I write down the definition of work, so that would be the derivative with respect to time, acting on the integral of f dx. And you have to remember, what was the little trick I had for getting this formula? I had to check for mathematicians, and then I divided by dt, and I multiplied by dt. All right. So I basically am turning it back into an integral over time. And now instead of integrating over x initial to x final, I'm going to integrate over time initial to time final. And now I know how to take the derivative, because what I have here is a derivative of an integral. It's like doing the derivative of the integral of t. Well, the integral will be t squared over 2. The derivative turns it back into t. The derivative and integral undo each other. And what I simply get is the following formula for power. Power equals, in one dimension, it's equal to the force times the velocity in one dimension. And this should be the force along the motion. Okay? The force along the motion times the velocity gives you power. So let's use this to evaluate a simple problem. Just go ahead and write that over here. Power is force times velocity. Just a word of warning, don't confuse power with momentum. Momentum is a vector quantity. Power is a scalar quantity. Unfortunately, we use the letter P for both of them oftentimes. Personally, here at JCC and these courses, I usually just write out power, and then it's clear. But there you go. Because P can also refer to pressure. So in thermodynamics, we'll have power and pressure, and you could have momentum. We don't normally, but you could. All right. A nice little example. Imagine there's a bicycle, and you're on it. And you're pedaling and pedaling and pedaling as fast as you can. Spinning, 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 spinning. And there's wind into your face. Okay? So what happens is, or actually, you don't even have to have wind. You could imagine it's just air. Maybe let's just do that. It's just air. Okay? But as you pedal faster, 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 you're developing, from your point of view, it's like the air is coming at you. And so you're feeling wind resistance. And when you pedal slowly, there's just a little bit of wind, no big deal. But the faster you go, the drag force will increase, and it gets harder and harder and harder. And eventually, you can pedal as fast and push as hard as you can on the pedals with as much force as you can generate, but you won't be able to keep speeding up because basically every bit of energy that you add into the bike, the wind will suck that energy out in the form of negative work. So what I want to know is, in order for you to pedal at some good speed, let's say 15 meters per second. Let's say you pedal at 15 meters per second and you're at terminal velocity. You maintain a constant 15 meters per second. What is the power that you have to supply to counteract the effects of gravity? So in that situation, basically, the power that you add is immediately dumped into wind resistance. So your power is going to be, at least up to a minus sign, the same as the power of wind resistance, which is drag force. So the force in this case that we're going to study is the drag force. Remember, that was 1/2 gamma times the area times the density, rho, times the velocity or the speed squared. I think I have all the little pieces there. Now, as is typical, we can take gamma to be about 1/2. Let's go ahead and assume that the cross-sectional area of you and your bike is about 1/2 meter squared. The units will work out. And then let's assume you're trying to pedal at 15 meters per second squared. And the units will come out in newtons when it's all said and done. All right? So 15 squared is 225. 2 cubed is 8. 225 divided by 8 is going to be a little bit less than 3. Let me grab my calculator here. 225 divided by 8 equals what did I say? 30, I meant. So it's 28.12. So the force, the drag force, I'm calling this drag force, let's call it D. The drag force is 28.12 newtons. Get that right? Yes, 113. Okay? So as you're pedaling, this drag force is pulling energy out of the bicycle and you, the system, because the force is opposite the motion. So it's going to perform negative work and it's going to have a negative power associated with it. You, on the other hand, have to compensate by replacing that energy. So you are going to produce a positive power. So finally, our formula for the power, you must supply equals force times velocity. So 28.13 newtons times your velocity of 15 meters per second. And that will come out in watts. So if I do that, multiply it out times 15, and I get 422 watts. Okay, so that's kind of a nifty little formula. Some of the times we do all these things, and the formulas are really gross, and they get really big. Power, turns out, for mechanical power, that's what this is, has a nice little formula, force times velocity. All right, the other thing I wanted to do in this video was to write down, at least once, the full 3D version of the work energy theorem. And so in 1D, we have the following. Kinetic energy equals 1/2 the mass times the velocity squared. Sorry, I'm jumping the gun. 1/2 times the mass times the velocity squared. In 3D, we're going to have 3 types of velocity. Velocity in the x, velocity in the y, and the velocity in the z. So the kinetic energy, it receives contributions from all of them. So it's equal to 1/2 the mass times the velocity in the x squared plus velocity in the y squared plus velocity in the z squared. That's nothing other than, I can write this a couple ways, it's 1/2 the mass times the magnitude of the velocity vector squared, or a convenient way to write that is 1/2 times the mass times velocity vector dot product with itself. Okay, so this is the 3D version of kinetic energy, or at least translational kinetic energy, energy associated with moving around, translating from side to side in space. When we talk about rotations, we will also have a rotational kinetic energy. I'll develop that when we get there. All right, so I'll write that over here. Kinetic energy equals 1/2 the mass times v dot v. But really, you just think of it as each separate type of velocity contributes to the kinetic energy. In one dimension, the formula for work was the integral of f dx from x initial times to x final. And then it shouldn't be too much of a surprise, given the example we did with gravity, where there was a dot product, you could kind of massage it into a dot product, that this is going to involve a dot product. But it's not going to involve a dot product between 2 big vectors, macroscopic vectors. In fact, what you have is the following. Let's imagine we have some random path in 3D. Okay, so you can imagine there's some little path. And so along the path, you have a little vector, dr vector. And you can imagine that when you're moving around, there's a force right here with some angle, theta. And over here, it could be, things change as you move around. It's all continuously changing. Over here, dr is like that. It's a different direction, maybe, in even magnitude. And maybe over here, the force is like that. And so the angle is different. So as you move around a path, the force could be continuously changing. Your path could be continuously changing. So the magnitudes of everything are changing, and the angles are always changing. Everything's always changing. And so when you do the integral to sum up all the bits of work, what you'd want to do is kind of apply this at each little patch. And you'd want to rewrite this, and it turns out the appropriate way to define work in 3D. So this was for 1D. For 3D, or in generality, work equals the integral from the initial position to the final position of the force as a function of whatever it's a function of, as a vector, and you take the dot product with dr vector. Now, for us in this class with the technology that we have, we aren't going to do integrals like this because that's a Calc 3 kind of problem. But it's important to kind of see where it's all coming together. The idea is basically in each little patch you could do your high school physics, force times change in displacement with the cosine of the angle. And then at each little region you'd want to adjust your displacement, adjust the angle, and adjust the force. And then you would just kind of add them all up to get the total work, and that's going to build up this integral. Okay, so if you've had Calc 3, I believe some of you have, you will recognize this is a line integral from one point to another. And if you haven't had Calc 3, then that's what this is. It's a line integral from point A to point B. Again, the examples we have are objects going on a ramp or simple things. So that's okay. All right, that's it for this video.